Welcome back to week 7 of the Thermodynamics course, and I'm again sorry for a certain delay and postponement of some series of sessions, 3 sessions if I'm not wrong. And it has primarily done because I was out of station, primarily out of country for attending an important conference, because of which I was not able to conduct these sessions. So I am very sorry for that. I am very sorry for any inconvenience caused to the students and the course handlers back in the NPTEL. I am sorry for that, and I will make sure that I cover up all the sessions as per the all the set scheduled sessions and complete the topics that were discussed and get back to the usual proceedings that we have in these sessions. Okay, so once again I'm sorry, and let's just get back to the course. Okay, so in week 7 we start with discussing a problem, one problem that was left in the previous week's discussion. That is one problem on the steam tables. I will briefly go through it, and moreover let me just again reiterate our regular agenda. That is, briefly go through all the topics that were discussed by Professor Anand in the lectures. Of course, I will not dive deep in each and every concepts. For that, I suggest that you go through a lecture. There are best sources for it, and of course the corresponding textbooks suggested by Professor Anand. And after this discussion, we will take some questions that are relevant to the assignment, as well as to the relevant to the questions that may come in your examination. So we'll look into that, and then we can end today's session. Okay, so with that, let us start. So the first question here is given as, and it's an example problem, so you don't need to solve it. I will just go through it once, and then if you have any doubt you can ask, or you may pause the video and just try it out yourself. Okay, a closed rigid vessel contains 1 meter cube of steam at 7 bar and 500 degrees Celsius. Okay, so these are the crucial information. That is, it's a rigid vessel. I'm sorry, it's a rigid vessel. Volume is 1 meter cube, and the initial pressure and temperature are 7 bar and 500 degrees Celsius respectively. The steam is now cooled to a state where the pressure is 0.5 bar. Okay, so again the second state here is 0.5 bar. Determine A, the temperature at which the condensation may first occur. Okay, second is the fraction of the total mass that will condense after the process has been undertaken, that is, it has been cooled to 0.5 bar. Finally, the volume occupied by the saturated liquid at the final state. Okay, so this is a question. It may seem a bit tricky at first, but I think if you go step by step, it will become quite easy to understand. Okay, so let us understand the first part. It is the temperature at which the condensation may first occur. Okay, and keeping all the things in mind, a schematic diagram, let me just scroll down a bit, can be shown here. That is this one. Okay, so it states that okay, for that let us first look into the question. Okay, I am sorry, I am just okay. So the first thing is the information. So volume is 1 meter cube, initial volume. Final pressure is 0.5 bar, initial pressure is 7 bar, and or 0.7 megapascal, or initial temperature is 500 degrees Celsius. So the first thing to look is whether the steam is at superheated state or at saturated state. Okay, so of course there is a certain relevance in the question itself, a hint in the question itself, but still let us try a brute force method to look into whether the steam is at superheated state or saturated state. So if you look in the steam table, I am not going to that for now, but if you look into it, you'll see that at 7 bar the saturation temperature is, for steam of course, is 151.2 degrees Celsius, which is less than T1, it is 500 degrees Celsius. So it states that the steam is at superheated state. Okay, and moreover in the question, since it states that the condensation is about to occur, so it means that it inherently means that the steam is at superheated state. Okay, so that's the reference or hint that I wanted to show you in the question. Okay, so now we can start to draw the schematic diagram. Okay, so the first diagram is the diagram is shown here. Again, the TV diagram and the liquid vapor dome is I'm sorry, mentioned here, and the initial state is at superheated state. Okay, so the first question is the temperature at which the steam will first start to condense. Okay, the crucial hint that we get from the question is that it's a rigid vessel. So rigid vessel would inherently imply that the process must be a constant volume process or an isochoric process. Okay, so for in a TV plot, this process can be shown as a vertical line coming down from one to the saturated vapor line. Okay, so the moment at the or the point at which this line touches the saturated vapor line is the point where the steam will first start to condense. Okay, so it is at this point we need to find the thermodynamic properties. Okay, we need to find thermodynamic properties at this point. Okay. So by now you might have understood that the general procedure that we need to follow. The first is to find the thermodynamic properties from the superheated steam table at point 1, that is 7 bar and 500 degrees Celsius. So from that you get that the internal energy at that point is 3127.4 kilojoule per kg. The specific volume is 0.5176 meter cube per kg, and the enthalpy is 3482.35 kilojoule per kg. So the parameter of interest, or I would say more importance, is the specific volume, because it is something that remains constant. Okay, for an isochoric process. So it is the parameter that we will keep constant and find the corresponding values at the saturation state to find the corresponding temperature at point 2 at this point. Okay, so it is point 2. Okay, so that's the idea. Now to find the mass of the steam, what we need to do is, given that we know the specific volume and the total volume of the container, we can easily find the mass. So the mass of the steam inside the container is given by the total volume by the specific volume. So 1 by 0.5175, that turns out to be 1.93 kg. Okay, so our task is to look into the saturated steam table and find the value of temperature, because if you go back to the question, it is specifically mentioned to find a temperature. Okay, so find a temperature. So we need to go into the saturated steam table and find the value of temperature for which the specific volume is 0.51765 meter cube per kg. Okay, so that's the hint. So let me again repeat it. So in order to find a temperature at which the steam first starts to condense, and since the specific volume remains constant for this isochoric process or this rigid vessel, so we need to find the temperature from the saturated steam table for the corresponding value of V, or the specific volume of 0.51765 meter cube per kg. Okay, so that's the task. So if you look in the steam table, it's not necessary that you will directly get the value of temperature for this exact value of specific volume. So you might need to do some kind of interpolation. Okay, so that's exactly what I have done here. So what I found from the steam table, saturated steam table, is that this value of specific volume, this V is 0.5765, lies between 0.6680, whose corresponding temperature is 130 degrees Celsius, and 0.5085, whose corresponding temperature is 140 degrees Celsius. So it means that our specific volume of 0.51765 would lie between 130 and 140. And even if you look into the problem, like if you're in quite a hurry and you need to solve it fast, you will understand that 0.5765 is quite close to 0.5085 than 0.6680. So temperature around 130 would be around 140 would be a much better approximation. Okay, but still, since we have ample amount of time for this session, let us try to do the interpolation. Okay, so we have that. So it would imply that this slope and this slope should be equal to, or you can even do like this slope and this slope as well, no worry. But in this case we have chosen like to equate this slope and this slope. Okay. So if you do that, you get 0.5085 minus 0.680 divided by 140 minus 130 equal to 0.5085 minus 0.5765 minus, so divided by 140 minus t. And if you do the calculations, you will get that T is around 139.42 degrees Celsius. As you can see that it is quite close to 140 degrees Celsius, but again, since we have time, I think it's better to find the exact temperature from linear interpolation. So we get the temperature at which the first condensation starts is 139.42 degrees Celsius. Okay, so that's the first answer. Let's look at the second question. So the second question is the fraction of the total mass that will condense. Okay, so I'll give you some time to think about it. Think about it. So the thing is, I'm sorry, okay, just give me 1 minute. Just 1 minute, that's right. Okay. Yeah. Just give me 1 minute. I'm sorry again. Sorry. Yeah. So the task is to find the fraction of mass that will condense. Okay. So it implies that after this process occurred, that is, the steam has cooled from 7 bar to a pressure of 0.5 bar. Find the fraction of mass of steam that will condense. Okay. So the second process can be shown as here, that is this line. So initial pressure was 7 bar. So now it has the temperature has reduced, or pressure is reduced to a pressure of 0.05 megapascal to this state, say state 3. I think I should what have let me just see what I have written. Okay, so I have, okay, so this I have taken as 2, so it would better like if that's 1, this is say 2, and this is say A, capital A. That would be better to remove any kind of confusion. Okay, so this is our final state, state 2. So pressure is 0.05 megapascal. Okay, so you need to find the fraction of steam that has condensed after the steam has pressure reduced from 7 megapascal to 0.05 megapascal. So again, you will understand by now that the parameter of interest remains the same because the process is isochoric, this constant volume process. So the specific volume, that is 0.5176, that is this one, will remain constant in this process as well. So the specific volume will remain constant from 1 to 2. So you can, what you need to do is, since it is inside the liquid vapor dome, because it is already condensed at point A, so definitely the next state after further decrease in pressure, the state of the steam will be inside the liquid vapor dome. So it is in the liquid vapor dome, so we need to take the aid of the saturation steam table. Okay, so what you need to do is, you need to find the corresponding value of Vf and Vg at this state, and then equate it to the specific volume at V1, that is the same as here V2, and use the formula V is equal to Vf plus X Vfg. Okay, so if you recall, let me just go back. Yeah, you need to use this formula. Okay, and since you need to find the amount of steam that has condensed, you need to specifically find the value of this one. Okay, you'll see how. So at P equal to 0.05 megapascal, from the saturation steam table we have, for steam we have Vf as 0.001029 meter cube per kg and Vg as 3.3625 meter cube per kg. Okay, so we have V1 or V2. I think it would be better if I write something like this, so it makes more sense. So it is equal to V2 as well. Okay, so V1 or equal to V2 is equal to Vf plus X Vfg. Okay, so X would be equal to V1 minus Vf divided by Vg minus Vf, that is Vfg. So if you substitute the numerical values here, I'm sorry again, here you will see that X turns out to be 0.1536 or 15.36%. So X, if you recall, was the dryness fraction, that is the amount of gas or the gaseous state in the mixture. Okay, so but now we have been asked to find the amount of steam that has condensed. Basically it has converted back to the liquid form. Okay, so it is basically 1 minus X. Okay, so X, if represents the amount of gaseous state in the, or steam inside the, or the amount of vapor in the mixture, so we need to find the amount of liquid. Okay, so it would be, the fraction of total mass that is condensed would be 1 minus X. Okay, so if you just look into this formula, I have even simplified it for your understanding. So the total mass of the total mass that is condensed would be mf by m. Okay, or m minus mg by m, right? Because mg plus mf is equal to total mass of the mixture. So if you divide it by m, we will have 1 minus mg by m, and mg by m is x. I'm sorry. So if you do that, you will get the fraction of mass that is condensed to be equal to 0.8436 or 84.36%. Okay, so I hope this is clear till now. Okay, let us go to the third part. So third part is volume occupied by the saturated liquid at the final state. Okay, so again it's quite simple. So saturated liquid, then you need to multiply the mass of the total mix liquid times its specific volume. Okay, so if you let us go down, so we will have that the volume of fluid would be specific volume of the I'm sorry, the specific volume of the fluid times the mass of the fluid. Okay, so we have that the specific volume of the fluid is 0.001029 if you just go back here, yeah, from here, and the mass of the fluid at the final state would be, if you recall, it is 84.64. Oh, I'm sorry, it's 64, right? So I have made a mistake here. It would be 64. Sorry. So 84.64% of the total mass of the mixture, right? So we have 0.8464 times 1.93 because we found out the total mass of the mixture from the initial state. So this is the mass of the fluid times the specific volume of the fluid. This is this one. So if you do that, you will get the volume of the fluid to be 0.00168 meter cube. Okay, so volume of fluid, not the mixture, but the volume of fluid in the mixture. Okay, so I hope this is clear till now. I will wait for 2 minutes just for you to take in the discussion, and then we will proceed further. Okay. So let's proceed. I hope this was clear. So let's proceed. Okay, so next question is a simple question but a thought intriguing question. So let us look into it. Of course, it's something that I feel, but it may not be the same for everyone. But let us look into it. Okay. So we have determine the specific volume of water at 220 megapascal and 400 degrees Celsius in meter cube per kg using first the steam table, second the ideal gas equation of state. Okay. So the thought intriguing part for mine was that just to see, because we know that steam cannot be taken as an ideal gas. Of course, in approximation of high temperature or in an extreme superheated state, we can consider or we can treat in a way the steam to be behaving as ideal gas, as we discussed in the initial part of in the previous lectures, that it can be, but of course there are some kind of what to say limitations because of which we cannot do that. But still, just to see whether the ideal gas equation gives us correct results or not, or what's the degree of incorrectness or degree of error, I'm sorry, in the calculations, it's a good practice to just see whether we can get similar results or not. Okay, so that's the thing. So we have pressure to be 20 megapascal and temperature at 400 degrees Celsius. So by the looks of it, first we need to check whether it is at a saturation state or superheated state. Okay, so from if you look in the steam table, for pressure equal to 20 megapascal, the saturation temperature turns out to be 365.8 degrees Celsius. And since 400 degrees Celsius is greater than the saturation temperature, it would mean that the steam is at superheated region. Okay, so that's again one thing that makes us feel comfortable in the sense that the results from the ideal gas equation would be a bit more correct, because since if it would have been in the liquid vapor dome, then use of this ideal gas equation to characterize steam, it would be completely useless. But since it is outside the liquid vapor dome in the superheated region where there can be some certain level of approximations made, then we can think that yeah, maybe ideal gas equation would be a bit helpful. But nevertheless, let us look into it. So from superheated steam table, for pressure at 20 megapascal and temperature at 400 degrees Celsius, we see that the specific volume to be 0.00995 meter cube per kg. Okay, and again I'm sorry for this beeping sound. It's an alarm outside my room and I don't know why it is been activated, but it will be handled soon. But again, sorry for the inconvenience again. So from the ideal gas law, you know that PV is equal to MRT, or P times small v is equal to RT. If you just divide mass by the volume, it will become specific volume. Sorry, mass divided by volume will be density, and volume divided by mass would be specific volume. So PV equal to RT. Okay. This is small v, and R here is the specific gas constant. Okay, that universal gas constant by the molar mass. Okay, and again I have to make it capital M. So we have specific volume V is equal to RT by P. So for water, we have the molar mass to be 18. So R would be 8.314 divided by 18, or 0.4619 kilojoule per kg Kelvin. So if you substitute these values here of the temperature and the pressure as well, you will have V as 0.4619 times 673 Kelvin divided by 20,000 kilopascal or 20 megapascal. So we have specific volume V as 0.015543 meter cube per kg. So we can see that of course there is a certain level of error, and in some ways it can be considered to be highly significant, but still it's not that far apart. It's say 0.06 meter cube per kg greater, right? Greater than the value approximated by the, or value I would say calculated from the steam tables. Okay, so of course the value from the steam table is much more accurate and much more acceptable, but still from the ideal gas equations we are not that far off. Okay, again, I might seem quite it might be quite wrong from my end to say it is not that quite far, but I'm just saying, since it is the state of the steam is in the superheated region, the values are still comparable. But if it would have been in the liquid vapor dome, then there might have been much more discrepancies in the values. Okay, so I'm just checking it, just give me 1 second. Yeah, 0.006 actually, 0.006 divided by 0.00995. Okay, uh, quite a bit of error actually, but yeah, of course the error is still there, but the values are still comparable. That's what I wanted to show. But yeah, let us proceed. Okay, so with that, again, if I recall, there was one more exercise of finding the same values using the compressibility chart. So again, as an exercise, you can try that out. One more thing that you can do is consider using the values of steam at very high pressure, very high temperatures specifically, and see whether you are, say for example, at even at this 20 megapascal. Let me just, yeah, find the specific volume at very high temperature. Say what is the highest value of temperature is being given in the steam table, super steam table, and then compare it to the value obtained from the ideal gas law, and then you can see whether at high temperatures whether you get a much more comparable values of these thermodynamic properties from the ideal gas law and the steam table. Okay, it's just an exercise that you can try out, but this is completely upon your interest. Okay, but the thing that you should try out is the part that Professor Anand discusses about comparing these values by finding this specific volume from the compressibility chart. Okay, so that's an exercise that you can try out. I have left it for you, but you can try that out. Okay, so now let us come to the theory part for today's discussion. That is the first law of thermodynamics for flow processes. Okay, so I think I should directly start. Let me just recapitulate the concept that I have previously discussed when it becomes relevant in the discussion that we have today. Okay, so let us start. So we have that from the first law of thermodynamics for a thermodynamic process, we have delta Q is equal to dE plus delta W. Okay, and dE, that is the energy of the system, can be dissociated into its internal energy, its kinetic energy, and its potential energy. Okay, and primarily into its kinetic energy, potential energy, and the internal energy. And we have we have seen that for for most of the thermodynamic problems, the internal energy was the most relevant form of the energy of the system. Okay, primarily because there was no flow related properties where there was a significant change in the velocity of the thermodynamic properties. Okay, I'm sorry, where there was no significant change in velocity for the system. That's why, so the most relevant form of energy was the internal energy. But we will see that as we discuss for these control volumes or open systems, the change in the kinetic energy also becomes a bit more relevant. Okay, as well as the potential energy. But then also we'll see that the highest contribution of this change in the energy of the system is again primarily given by the change in internal energy, but that's not a generalized case. But for most of the problems you will see that. Okay, even in the flow processes. Okay, so let us try to see whether we can derive it, how we can derive it. Okay, so if we divide the equation by delta t and take limit as delta t tends to 0, we get the rate equation for the first law. Basically, this is the unit of all these properties here is in terms of joule or kilojoules or calorie, like if you want. But if you divide it by time, then we get the rate equation. This is the rate of change of these properties. Okay, so we have we have q dot is equal to d by dt plus w dot. So it is the rate of change of heat is equal to rate of change of energy plus the rate of change of work. Okay, so let us take one example for applying this to a thermodynamic system with a no flow. Okay, no flow basically means there's no evident mass transfer. Okay, so consider a bulb. I'm sorry, just give me 1 minute. Okay, consider a bulb attached to an electrical output, and say it has been uh, it has been kept on for a long time. Then for a steady state, the rate of change of energy of this system becomes equal to zero. There's no change in the uh, energy of this system. Okay, so d by dt becomes equal to zero. So we'll have that q minus w equal to zero, or q is equal to w, or w is again we can evaluate it as being equal to vi. That is a standard equation for these electrical systems. Or if we multiply it with time, we'll get the net work done. It is vi times t. Okay, so it is a very simple example of applying the rate equation or the rate form of the first law of thermodynamics to a non-flow thermodynamic system. Okay, so again, sorry, just give me 1 minute. Okay, meanwhile you can look into the equations. Maybe you okay, I'm sorry for this frequent pauses. So let us proceed further. Okay, so we have, yeah, this is the rate for the energy equation. Now let us consider mass conservation. So I don't know till now whether we have introduced mass conservation or not, but let me just give you a brief idea that for any engineering systems, uh, there is there are three conservation laws that are primarily used always to analyze this kind of systems. Okay, so there is the mass conservation, the momentum conservation, and the energy conservation. Okay, so for the sake of this course, this thermodynamic course, we will be only be dealing with mass conservation and mass conservation and energy conservation. Okay, momentum conservation also becomes very crucial in the scope of fluid mechanics, where all these three conservation laws again specifically in fluid mechanics, it is the mass conservation and the momentum conservation that becomes more relevant. But these three conservation laws go hand in hand. Okay, but for the scope of this course, we will be primarily discussing about mass conservation and energy conservation. Okay, so mass conservation is given by this equation, that is the rate of change of mass inside the control volume would be equal to the summation of, or basically the net mass influx minus minus the net mass outflux. Okay, so for example, like if there is a, let me give you one example. So for example, if there is a bucket, okay, what example of mass conservation? Okay, so if there's a bucket and there's a certain level of liquid inside the bucket, and there's a tape being switched on, turned on. I think that would be a more correct. Okay, and water is being poured through the tape inside this bucket. Okay, and there is a certain hole, a small hole inside the bucket, or at the bottom surface of the bucket. Okay, so there's a certain amount of liquid uh, oozes out of the bottom. Okay, so the mass conservation becomes, I'm sorry, the mass conservation becomes relevant now, in the sense that the rate of change of this mass of liquid inside the bucket is given by the is equal to the net mass influx, that is from the tape here, minus the net mass outflux, that is through this hole here in the lower surface of the bucket. Okay, so if, for example, if the net mass influx is greater than the net mass outflux from the bucket, you will see that there will be a certain mass accumulation inside the bucket, right? So it will mean that if Mi is greater than Me, then this will become positive. So basically mass will grow inside the bucket. Okay, and similarly vice versa, that if mass influx is lower than the mass outflux from the hole below the bucket, then Mi minus Me will be less than 0, so mass will reduce inside the bucket. But again, there is an interesting case, that if Mi equal to Me, then what would happen? Then dm by dt inside the control volume would be equal to 0, so that mass inside the bucket won't change. Okay, so there's again an interesting case. Okay, so you can say that in that kind of scenario, the system has reached a steady state, because there is no change in the mass of the system with time. Okay, so similarly, the energy of the system does not change with time. You will say that the system has reached a steady state. Okay, so again, this equation can again be simplified for a single inlet and outlet. Let dm by dt Cv is equal to Mi minus Mi dot minus Me dot. Okay, so this dot will, at least in this class, will inherently imply the rate properties, that is dm by dt, or all properties divided by time would be shown as a dot over that property. Okay, so the volume flow rate is given by velocity times the area, or like if the velocity changes with velocity changes spatially, then we have, like with spatial coordinates, then we have integration of v times dA. Okay, but for most of the problems this will not become relevant, at least in this thermodynamic course. So you can easily take volume flow rate to be velocity times area. Okay, and the mass flow rate to be density times the volume flow rate, or rho Av, or 1 by specific volume, that is small v times Av. Okay, where v bar over the velocity v basically represents an average velocity. Okay, so similarly, the energy equation for a control mass can simply be given as d by dt Cm equal to q dot minus w dot. Okay, for a control mass. Okay, where there is no flow occurring. But if we take a control volume, that is the volume is fixed, I won't say fixed, but volume is specified. The specific volume is specified or fixed at a particular location, which may be deformable or rigid, but there is a certain amount of energy flux and mass flux occurring through the control volume. Okay, so we need to find the energy equation or the rate energy equation for the control volume. So that's our task. And again, I will not go to the derivation, but let us just go through the step and discuss the final form, or the complete form of the energy equation for a flow system. Okay, so we have, at a control surface, we have energy to be given as energy per unit mass to be U plus Ke plus P. Okay, and flow work done because of the flow to be PV times the mass flow rate, m dot. Okay, so how it is derived, I think I leave it to you as an exercise, or for you to look into the lectures to see how it is derived, but you can look into it. Okay, so it's something, this is the additional thing that comes when discussing about this flow system, that is the work done because of the flow of the liquid to the control volume. There's that also has to be considered. Okay, so that's why this additional term comes into picture, and you will see how it affects the energy equation. Okay, so we'll have that the total energy interaction would be again E plus PV, or U plus PV plus half V square plus ZZ. Okay, GZ. Okay, so now U plus PV, if you recall, was equal to the enthalpy H. Okay, so again, this equation, how it came, there is a detailed discussion about it in the lectures, and even if Professor Anand, if he would have not taken this in the lectures, there is a very thorough discussion of this in the textbooks. Okay, so I suggest that, of course, it's a good practice for you to know how it has been derived, and there is a thorough discussion on it, like how this work done because of flow energy comes into picture for flow systems. But for the sake of saving time and for the sake of relevance to this particular class, I would just skip that part, and maybe Professor Anand has also skipped that part in the lectures, I'm not quite sure. But if he has skipped, even if he would have skipped in the lectures, I would kindly suggest that you can go to the textbooks, any thermodynamic textbook that discusses about the steady flow energy equation. They will surely discuss how this additional PV term becomes relevant for flow systems, okay, in the energy conservation. So now, yeah, so this is the net energy interaction with the flow, okay, that we get. Let me just show, yeah, this one. Okay, so there's the new parameter that comes is enthalpy, like rather than internal energy. Now we have additional parameter that is enthalpy. Okay, so for the energy equation, for a rate energy equation for a control volume, then becomes Q dot Cv minus W dot Cv plus, yeah, these are the control for energy change for a control volume. But since there is a mass flow, or a mass flow there is a mass flow, net mass flux to the control volume, it will also have a corresponding energy that it that is, there will be a corresponding value of energy that corresponds to this mass flux. Okay, so there will be relevant energy flux as well. So that's why that these terms become relevant. Okay, so with that we have Q dot C minus W dot Cv to be equal to Mi dot this Hi plus Vi square by 2 plus Gzi minus Me dot He plus Ve square by 2 plus Gze. Okay, so this workflow, I think I can highlight it with some color. So this one is your PV. Okay, this is what we can incorporate it in these terms, this mass influx and mass efflux or outflux terms, and write it as in terms of enthalpy. Okay, as shown here. Okay, so this will have your U plus PV, and it will have, or let me just be specific, it will have UI plus PI VI, it will have UE plus PV. Okay, so with that in mind, now if we generalize this for multiple inlets and outlets, we'll have d by dt Cv equal to QCV minus WCV plus summation of Mi times Hi plus Vi square plus Gzi minus summation of Me dot He plus Ve square plus Gze. Okay, so it basically means consider all the energy interactions because of the mass flow rate or the mass flux to all respective inlets and outlets. Okay, so this gives us the final form of your energy equation for a control volume. Okay, basically the first law of thermodynamics in rate form, that is divided by time, for a control volume. Okay, so this is your relevant equation. And as if you recall, in the very first discussion for this first law of thermodynamics for this course, I mentioned that whenever there is a flow, like initially we had internal energy U to be the relevant parameter or relevant energy characterizing parameter in the first law of thermodynamics. But I mentioned that if the system has flow as well, one other parameter, that is enthalpy, becomes more relevant. So we'll see that of course there is an internal energy change inside these equations, but since we incorporate the flow energy as well, or the work done from the flow energy as well, and these two sum up to be the enthalpy, that's why we see that in an essence the change in enthalpy becomes a much more relevant parameter than the internal energy for these flow systems, okay, or control volume. Okay, so that's something that you can keep in mind. But of course, if you break it down again, you will get back your internal energy and flow energy. Okay, so the one way to check whether your equations are correct or not, just consider that if there's no mass transfer, there is no mass influx and no mass efflux or mass outflux, so these two terms will be zero. So you'll again get back your initial equation, that is d by dt cv equal to q dot minus w dot. It is the equation for your control mass. Okay, it becomes exactly the same if there is no mass flux through the control volume. Okay, so this is the energy equation. So this is something that you can remember, and like it's a good practice if you are able to recall it. Okay, but our interest lies in the steady state form. Okay, because most of the problems that you will see for this today's discussion as well, you will see that we are generally discussing about the steady flow systems. Okay, so as you can see, if you discuss steady flow, then this term will become equal to 0, right? So let us go step by step for, and then that form the equation where the rate of change of the energy of the control volume is equal to 0, or basically the system is at steady state. That form the energy equation is known as the steady flow energy equation, or also known as SFEE. Okay, it's a very popular equation for basic thermodynamics, classical thermodynamics. So it is something that you can recall. Okay, so if you do that, let us go to an energy equation that this d by dt becomes equal to 0 for steady state. So we are left with this equation. It is q dot minus w dot plus summation of mi dot hi plus vi square plus dzi minus summation of me dot he plus ve square by 2 plus gze. Okay, so again there are certain level of manipulation that can be done, like you can keep all the positive terms in this equation at one side and take the negative terms in the other side, so that you're left with this q and mi, these terms in the left hand side, and this w and this me terms in the right hand side. Okay, this again another form of your steady flow energy equation. And as I mentioned, if you go to the mass conservation, if dm by dt cv equal to 0, that is mass influx and mass outflux is equal to 0, so we'll have summation of mi is equal to summation mi dot is equal to summation me dot. Okay, this is one approximation, but for example, it can be simplified even further. So if you have only single inlet and single outlet, okay, again understand the specifics. If there's only a single inlet and single outlet, you will have mi dot is equal to me dot is equal to a certain value of mass flow, that is m dot, say, and you can then divide this mi dot by all the terms. Then you will have q minus w plus hi plus vi square plus gzi minus he plus ve square plus gzd. Okay, so I think it will just be better if I just write the final form. So if that's the case, then I think I can maybe write it here after this step. Okay, so we can write something like q plus hi plus vi square by 2 plus gzi equal to w plus he plus ve square by 2 plus gze. So this is the steady flow energy equation for a single inlet and outlet. Okay, sorry, let's use a proper box. So this is the steady flow energy equation for a single inlet and outlet. Okay, so this is not, so generalized form would be this equation, but for single inlet and outlet, this can be simplified to this form. Okay. So just okay. So that's the, if it's understood now. So let us proceed. Okay. So now we will look into different kinds of thermodynamic systems or thermodynamic devices where we can use the steady flow energy equation, or I must say where we will try to find out the steady flow energy equation for different type of thermodynamic devices or thermodynamic processes. Okay. So I would say that an ideal, before like directly using the special form of the energy equation like directly for a particular process, like something like if you know that for a particular process the energy equation has this specific form, I would suggest that you just don't start using the equation directly. Okay. A better practice would be start with the complete steady flow energy equation or SFEE, then cancel out the terms that are not relevant for the particular problem, and then deal with that final term that you are left with. Okay. So if you are able to perfectly replicate the same scenario that we have same specific scenarios that we have discussed in the class, then there's very good. But there can be scenarios in the examination where the question might be a bit tricky, like for example, in a certain device they may add say heat addition, where usually in general case we do not consider, so you may be left out with a important term from the energy equation that should have been relevant for that particular question but has been left out by you because in the generalized equation we are not considering heat transfer. Okay. So there are some certain nuances that you need to understand before directly applying the energy equation for a particular process, but a general idea or a good practice would be to start with the complete energy equation and then cancel out the terms that are not relevant. Okay. So I hope that is clear. So let us start with the adiabatic throttling process. Okay. So for an adiabatic throttling process, again in a steady state case, du by dt term is equal to 0. Adiabatic would imply there is no heat interaction, and for throttling process there is usually no work done. Okay. So there is no work done, or basically it's not a work generating process, throttling. Okay. So we're left with these two terms, that is the mass and the energy influx and the energy outflux terms. Okay. So if we consider single inlet and outlet, okay, if we consider single inlet and outlet, then we'll have mi equal to me, mi dot equal to me dot equal to some m, then this term can be cancelled out from both the sides. Okay. So if you just simplify it even further, you will have that hi is equal to he plus ve square by 2 minus vi square by 2 plus gze minus zi. Okay. So for most of the cases, this change in a potential energy is very very less. Okay. So this is equal to 0, and for this throttling processes, as a first approximation as mentioned here, this term, this vi square by 2 minus ve square by 2, can be neglected. I'm not saying that the difference is always equal to 0, but I'm just saying that the very magnitude of these terms, that is the enthalpies, are much higher than the difference between VE and VI. Okay. That's why we can consider this term to be almost negligible compared to this enthalpies, and that's why this can be neglected. Okay. So the generalized form of your throttling process, or the generalized form of the energy equation for a throttling process is given as Hi equal to He. Okay. Or the net change in the enthalpy is constant. So for an ideal adiabatic throttling process, the enthalpy must remain constant. Okay. So this is an important outcome from the energy equation for a adiabatic throttling process. Okay. But as I mentioned, there might be scenarios in your specific question in the exam where there might be a significant change in the energy, in the kinetic energy. So you might need to consider it, but usually that's not the case. But for your specific question, there might be a significant change in kinetic energy. So and ideal practice is to start with the complete from the energy equation. Okay, so let us now look into turbines and rotary compressors. Okay, so this is turbines and motors. So if you consider an adiabatic system, again let us start with the complete energy equation. So if you recall, or if you look into it, these turbines and compressors, okay, these are sorry these are work producing and work consuming devices. Okay, what turbines are work producing devices, compressors are work consuming devices. Okay, so the work term is of high relevance in this kind of thermodynamic systems. Okay, so if we consider just one second. Just one second. Okay. Yeah, so if you consider it to be an adiabatic system, there is no, again if there is no relevant heat interaction, then for from the steady state energy equation, again for steady state d by dt term would be equal to 0 and net heat interaction would be equal to 0 if we consider it to be adiabatic. Okay, so but the work interaction term will not be equal to 0 as a throttling process, because the work is a term of relevance in the context of this turbo machinery, these turbines and compressors. Okay, and energy flux terms would again remain. Okay, we'll see what terms we can cancel out. So from mass conservation, we will have dm by dt is equal to 0 for steady state, and we will have mi, summation of mi is equal to summation of me. Okay, and if we again simplify a bit further, for single linear outlet, we will have mi dot is equal to me dot equal to m dot. Okay, so we will be left with this equation is 0 equal to minus w dot this plus m dot hi plus vi square by 2 plus gzi minus m dot he plus vi square by 2 plus gzi. So if you divide by m dot, okay, I think if you can divide, also divide it by it, but it's not done here. So we will have w dot as mi dot m dot times hi minus he plus m dot vi square minus vi square by 2 minus mg zi minus zd. Okay, so you will see that for most of these compressors and turbines, the change in the potential energy and the kinetic energy are mostly negligible compared to the net change in the enthalpy. Okay, so these two terms are usually almost equal to 0, or I would say of very less magnitude compared to this change in enthalpy. Okay, so we'll have w dot as m dot hi minus he. Okay, so the net work interaction is given as m dot hi minus he. So this is the steady flow energy equation for your rotary devices, that is turbines and compressors. So now we are again left with nozzles and diffusers. So you may ask, like, is it always the case that this kinetic energy and potential energy, all these terms are always negligible? So yeah, that's your counter argument for you, that is these nozzles and diffusers. So if you see here, these are devices where the both this energy in that is heat interaction and work interaction are of not that much relevance. Okay, but the thing of relevance here is the velocity. So if you recall, for subsonic flows, again I'm going to the very specifics, but let us just keep it that way. Okay, so for subsonic flows, nozzles are usually used to increase the velocity, and diffusers are usually used to decrease the velocity, okay, or increase the pressure. Okay, so in that case, since velocity is being changed, or the very purpose of this device is to change the velocity or affect the velocity, then these velocity terms that is given by these kinetic energy terms cannot be neglected, because these are terms of relevance. Right? These are terms of relevance in the equation. Okay, so again, if you start with the energy flow equation, that is d by dt would be equal to 0. Net heat interaction, work interaction are 0, because if you consider system to be adiabatic, then heat interaction inherently becomes 0, and this work interaction is 0 because these devices do not produce or consume any kind of work. Okay, of course there is some certain flow interaction that is being taken into consideration by the enthalpy term. Okay, so we are left with m dot times hi plus vi square by 2 plus gzi minus m dot he plus v square by 2 plus gzi. Okay. Again, and these nozzle diffuser are single inlet and outlet devices, because then only it becomes relevant. So we are not considering this summation term. Okay. So if you do that, then you're left with hi plus vi square by 2 is equal to he plus v square by 2 plus gze minus zi. And for most of the cases, so for example, if you just leave the nozzle or diffuser horizontally, there is no negligible change, there is no change in the potential energy, okay, or there is no perceptible change in the potential energy. So this term most of the times is almost equal to 0, okay, or it's not that relevant in this kind of case. So the equation of relevance for nozzles and diffusers are given by hi plus vi square by 2 is equal to he plus v square by 2, okay, or hi plus the inlet kinetic energy plus he plus the exit kinetic energy. Okay, but again, there might be scenarios in your question where your nozzle is tilted or your exit of the nozzle is at higher altitude, where the potential energy term may become relevant, but for most of the general cases, this is usually equal to 0. Okay, so the final device that we'll consider is the heat exchanger. Again, there is a very elaborate subject or elaborate topic to discuss heat exchanger, how they work, namely the heat transfer. So when you start discussing or talking about heat transfer, or read the subject of heat transfer, there is a very elaborate discussion on heat exchanger, or how they operate, how they are devised. All these things are very elaborately discussed there. So again, that is beyond the scope of this course, but if in a brief, if I want to say what heat exchanger mean, is that is again quite literal from their very definition. It is heat exchanging devices. Okay, so there might be a certain incoming fluid. There's two jets of fluid. That is, say this jet of fluid goes like that. I think I should use the diagram, some schematic representation. So let us use something like, just 1 second. Okay, so there might be a certain fluid passing through this duct, okay, and this fluid, I think this color is not correct, this color, and this fluid might be passing through this duct. Okay, so this is going through this duct. Okay, so it might happen that we want this ingoing jet, okay, this might be a hot fluid, okay, and we want to reduce the temperature of this fluid. Okay, so one way to do is that we can make it interact with a cold jet of fluid. Okay, so this fluid might be cold. Okay, so this hot fluid, when goes to this duct and interacts with this cold fluid that is passing through this duct, the temperature of this fluid will go down and temperature of this fluid will go up, because it's absorbing heat from this hot fluid. Okay, so our desired purpose is to cool this fluid. Okay, so we are getting a much colder fluid at the exit, but in the expense of this other jet of fluid becoming warmer. Okay, so it's again, so it basically what it's doing is exchanging, these fluids are exchanging heat between them. Okay, so that's the very purpose of heat exchangers. Like the fluid of interest, the fluid of interest can be, the temperature of the fluid of interest can be changed by the expense of a other fluid, which may not be that expensive or which may not be that quite relevant, but that's how the heat exchange is basically being done. And these devices are known as heat exchangers. Okay, and there are different configurations of heat exchangers. This is one example of counterflow. This fluid is flowing against each other. There might be scenarios where fluid may flow parallelly with each other. Okay, so there are different configurations and ways by which the heat exchangers can be designed or made. Okay, but that's the very principle of heat exchangers. Okay, so now you can see that in this case also the parameter of interest is enthalpy. Okay, so we'll see. So if we start from the energy equation, we'll have, if the entire device is insulated, then of course there's heat exchange being done. Let me just show it again. Heat exchange being done in this region, but the outer periphery of the control system is insulated. If that's the case, then net heat interaction is zero. This not producing any kind of work, so net work interaction again zero. So the relevant terms again are left with the energy influx terms. Okay, and you'll see that in this case as well, the, of course, I'm sorry, I need to show this as for steady state, of course. So in this case as well, the change in the potential energy and the kinetic energy are also usually equal to are usually equal to zero, or much less compared to the magnitude of this change in enthalpies. Okay, so only relevant terms that are remaining are this summation of mi dot times hi and me dot summation of me dot times he. Okay, so the concerned equation for these heat exchangers are given in this form. Okay, this is summation of mi dot hi is equal to summation of me dot he. Okay, and usually these heat exchangers are devices with multiple inlets and outlets, of course, because of different kind of fluids that has to pass through the ducts. That's why we cannot usually remove this summation sign. Okay, so this is the relevant form of the steady state energy equation for heat exchangers. So that's all for the theoretical part of today's discussion. So now let us directly go to the question and answer part. So I hope the question is visible. So this is the first question. So for that, I'll give you 2 minutes of time to look into the question and see which is correct, and then we can discuss the answer. Okay, so 2 minutes, you can start. So the question is, which of the following statements is true? A. In an unsteady flow process, the fluid characteristics like velocity, pressure, or density at spatial locations change with time. Second, in an unsteady flow process, the fluid characteristics like velocity, pressure, or density from one spatial location to another spatial location, change from one spatial location to another spatial location, but do not change with the passage of time. Okay, so which of the following statement is correct? Okay. So you know that for an unsteady flow, the parameters has to change with time. So the correct answer is option A. Okay. So you can now look at the next question. Okay. I'll again give you 2 minutes to discuss, and then you can tell me. The first law of thermodynamics for flow processes, also known as steady flow energy equation, is valid for which of the following types of fluids? Incompressible, compressible, viscid, inviscid. Okay. So look into the options and tell me which which are the types of fluids that are considered in the steady flow energy equation. Okay, I'll give you 2 minutes again to look into the question and then try it out. Okay. So if you look into it, you will see that while deriving the steady flow energy equation, we have not made any kind of specific approximation or type of fluid. Okay, so that's why this steady flow energy equation is valid for all these cases. Okay, that's why all these options are correct. Okay, since we have not made any kind of approximation while deriving the steady flow energy equation, so no need to consider any kind of specifics. So all these kind of considerations have been we can make while the steady flow energy equation will remain valid for all these kind of cases. Okay, there's no specific scenario that has been taken into consideration while deriving the steady flow energy equation. Okay, so now third question. So now the numerical part starts. Okay, so let's go to the question once. Air flows steadily at the rate of 0.5 kg per second through an air compressor entering at 7 meter. Again, I will just underline the relevant properties so that it's easy for you to take notes. Okay, so air flows steadily at the rate of 0.5 kg per second. So it is a mass flow rate when air compressor entering at 7 meter per second velocity, 100 kilopascal pressure and 0.95 meter cube per kg volume, and leaving at 5 meter per second, 700 kilopascal and 0.9 meter cube per kg. The internal energy of the air leaving is 90 kilojoule per kg, greater than that of the air entering. Okay, greater than that of the air entering. Cooling water in the compressor jackets absorb the heat from the air at the rate of 58 kilowatt. Compute the rate of shaft work input to the air in kilowatts. Okay, and find the ratio of the inlet diameter and the outlet diameter. Okay, so these are the two things I need to try out. So for that, I will say that I will give you say 5 minutes for part A. You can try it out, then we can discuss the solution. Okay, so yeah. Okay, so I think that what we can do is, since there are not many participants for today's class, so what I can do is I can discuss the solution now. But if say you are watching the video for your reference, what you can do is you can pause the video here. Okay, pause the video here, try out the solution from your end, and then take help from the solution that I have given. Okay, so if that sounds fine, I think we can proceed. Okay, so let us look into the solution. Okay, so all the relevant parameters I have already mentioned you. So let us directly look into the solution. So this is the schematic diagram of the solution. There's air compressor. This is the inlet condition. Sorry, these are inlet conditions. These are outlet conditions. So it mentions that we need to find the net work output from the air. If I'm not wrong, it is work input to the air compressor, right? It should be work input. Yes, of course, right. air compressor is a work consuming device, if I'm not wrong, right? So it should be work input. Sorry for the diagram, it should be work input. Yeah. And the net work output, or sorry, net heat interaction is also given, that heat absorbs heat from the air compressor, so it is given minus. And the outlet internal energy is 90 kilojoule greater than the inlet incoming internal energy. Okay, so with that we start again with the complete form of the steady flow energy equation. And since there are only one inlet and one outlet given by the number of parameters as shown here, so we can consider this equation and just neglect the summation part. Okay, so if you rearrange this equation, you will have W is equal to m dot u1 minus u2 plus p1 v1 minus p2 v2 plus v1 square minus v2 square by 2 plus g z1 minus z2 plus q. Okay, sorry for moving that fast, but this is the way. I'm just reading out the terms here. Okay? I'm just rearrange these terms so that I can separate out the work interaction. And if you see, you will get all these parameters are already mentioned in the question. So we will have mass flow is 0.5, u1 minus u2 is minus 90. Okay, because u2 is 90 kilojoule per kg greater than u1, so it's minus 90. p1 v1 is given, p2 v2 is given, and if you see, this p1 and p2 are in kilopascals. Okay, so it's again in kilojoule per kg, so you need to keep uniformity in the terms. Okay, uniformity in the units. So this v1 square minus v2 square by 2, if you just substitute by this velocity per second, velocity meter per second, then it is not in terms of kilojoules. Okay, it is in terms of joules only, right? So you need to multiply it by a factor of 10 to the minus 3, so that this term becomes in terms of kilojoule per second. Okay, kilojoule per second or kilowatt. Okay, that's why a factor of 10 to the minus 3 is multiplied. And this is where most of the students make a mistake, like all these terms are in terms of kilojoule per second, but this term becomes in terms of joule per second. So this term, there is a huge amount of error in the calculations. Okay, so you need to convert it into kilojoule per second by multiplying it at 10 to the minus 3, and there is no change in the potential energy, so it becomes equal to 0. Okay, and since there is heat being absorbed out of the system, so heat interaction is minus 58. So if you just calculate this, you will get W dot as minus 122 kilowatt, which implies that 122 kilowatt work input has to be done on the air compressor to sustain this flow process. Okay, so next was, if you look back, next was to find the ratio of the inlet and the outlet pipe diameters. Okay, it's again very simple. Why? Because you're already given the velocity and the specific volumes. Okay, so mass flow rate is A1 V1 divided by specific volume V1 equal to A2 V2. V2 is velocity divided by specific volume V2. So we have A1 A2 is equal to V2 V1 V2 divided by V1 times specific volume V1 divided by specific volume V2. Okay, so velocities are 5 and 7, and specific volume are 0.95 and 0.19. So we have and A1 would be pi by 4. Let me just write it. So A1 would be pi by 4 d1 square, and A2 would be pi by 4 d2 square. So if you divide A1 by A2, so this pi by 4 factor will cancel out, so we will be left with d1 by d2. Okay, so if you simplify it, then you will get d1 by d2 is equal to 1.89. Okay, so that's your solution. So I hope that's clear. Now let us look into the next question. Okay, sorry for moving fast. Since there are less participants in today's class, I think you can just move ahead in that manner. Okay, next question is, in a steam power station steam flows steadily through a 0.2 diameter pipeline from the boiler to the turbine. Okay, at the boiler end, the steam conditions are found to be P is 4 megapascal, temperature is 4 degrees Celsius, enthalpy is 3213.6 kilojoule per kg, and specific volume is 0.073 meter cube per kg. At the turbine end, the conditions are found to be P is equal to 0.35 megapascal, T is 392 degrees Celsius, H is 3202.6 kilojoule per kg, and velocity is specific volume is 0.084 meter cube per kg. Okay, so again this question seems to be quite simple in a way that all the parameters are already given. You are asked to find, or there's a heat loss of 8.5 kilojoule per kg from the pipeline. Calculate the steam flow rate. Okay, you need to find the net steam flow rate. Okay, so let me just you can kindly read through the question once, and I will discuss the solution then. Okay, so just you can pause the question here right now and then try it out yourself, and then we can discuss the solution. Okay, so now I'll discuss the solution, but for your reference, you can, after pausing the video, you can try the solution and then take the help of my solution. Okay, so for that we have, this is a schematic diagram of the question. Okay, so you may ask, they have not mentioned the work interaction, but turbine is a work interacting device. Okay, that's completely correct, but here the thing is that the steam is being flowed through the boiler to the turbine for turbine to start rotating. Okay, for turbine to start rotating and then produce work. Okay, but in this case our control volume is not the turbine. Okay, it's the region or the duct in between the boiler and the turbine through which the steam is passing through. Okay, so in that case, in the duct through which the steam passes through from the boiler to the turbine, there is no work interaction, there is no work done. Okay, there is no work consuming or work producing device, so there is no work done, no shaft work done. Okay, but there is a leakage of heat of 8.5 kilojoule per kg. That's what we have considered here. Okay, that's what we have considered here, and all the inlet parameters at the boiler end and the outlet parameters at the turbine are mentioned. Okay, so the task was to find the mass flow rate, if I'm not wrong. Right. So that's find the mass flow rate. Okay, so in order to do that, let us consider the steady flow energy equation. For this case, we will have H1 is equal to V1 square by 2 plus GZ1 plus Q dot is equal to H2 plus V2 square by 2 plus GZ2 plus W dot. And here again, you can indirectly take this equal to 0 because there's no work interaction being done. Okay, so in all these terms already mentioned. So the tricky part in this question is to find the velocities, because they have not mentioned. Let me just go to the question if I'm not. So they have not mentioned the velocity in the question, right? So to find the velocity, you need to find the mass flow rate, you need to have the velocity at the inlet or at the outlet. So velocity is a term of interest here, but since we don't have the velocity, but we have the diameter. Okay, we have the diameter, the area of the duct. Okay, so just at the inlet. So and we have the specific volume. So I think we can use these two to one way or another find the mass flow rate. Okay, so let us see how we can handle it. Okay, so for mass conservation, we use this again to find relation between this V1 and V2. Okay, so that we can apply that to get an equation of V1 or V2, like substituting either one of them and plug it back into the energy equation, and then see how we can find the value of V from the energy equation. Okay, so that's why we need to have V1 in terms of V2 or V2 in terms of V1. Okay, to find relationship between this V1 and V2, we use this mass conservation. Okay, so we have V2 as, from this equation we have V2 is equal to A1 by A2 times V1, velocity V1 divided by specific volume V1 times V2, specific volume V2. And since A1 is equal to A2, then we have V2 velocity is equal, velocity is 0.084 divided by 0.073. These are the specific volume times V1, or V2 is equal to 1.15 times your inlet velocity V1. Okay, so we have net work interaction as 0 and potential energy, net change in the potential energy to be 0. So we have the steady energy equation to be h1 plus v1 square by 2 plus q dot is equal to h2 plus v2 square by 2. Okay, or v2 square minus v1 square by 2 is equal to h1 minus h2 plus q dot. Okay, so if you just substitute the value of v2 in terms of v1, you will get v1 square times 1.15 square minus 1 square divided by 2 times 10 to the minus 3 to make all the terms in terms of kilojoule per second equal to 3213.6 minus 3202.6. This h1 and h2, these values are also given, plus q dot, and q dot is minus 8.5 because heat is being leaked out of the system. So if you do that, you will get this to be equal to 2.5 kilojoule per kg, and if you simplify it further, you will get velocity v1 is equal to 125.1 125.1 meter per second, and mass flow rate will again be given by a1 v1 times specific volume v1, that will be equal to pi by 4 times 0.2 square, this is diameter, times 125.1 divided by 0.073, or mass flow rate to be 53.8 kg per second. Okay, so that's how you do it. So now let us look into the next question. Okay, from now on I will try to move a bit faster because there are 2 more questions, if I am not wrong, that we need to consider. So yeah. A certain water heater, okay, there is a question. A certain water heater operates under steady flow conditions, receiving 4.2 kg per second water, 4.2 kg per second of water at 75 degrees Celsius temperature, and enthalpy of 313.93 kilojoule per kg. Okay, these are the inlet conditions, and the water is heated by mixing with a steam which is supplied to the water heater at temperature of 100.2 degrees Celsius and an enthalpy of 2676 kilojoule per kg. The mixture leaves the heater as a liquid water at temperature of 100 degrees Celsius and an enthalpy of 419 kilojoule per kg. Okay, so you need to find how much steam has to be applied to the heater per hour. Okay, so if you see, this is basically a example of heat exchanger where the water is being heated by mixing with steam with a higher temperature and enthalpy, and net temperature of the mixture is increased to 100 degrees Celsius and enthalpy is also increased. Okay, so you can see that the incoming temperature of the water is lower as well as the enthalpy is also lower, but the steam that is being used to heat this water up has a higher temperature as well as higher enthalpy. But you will see that after the mixing has occurred, the liquid water or the mixture of liquid and steam has a temperature of 100 degrees Celsius and has an enthalpy of 419 kilojoule per kg, which is a moderate value between these two. Okay, so this basically acts as a heat exchanger where the fluids are interacting with each other. Okay, so you need to find how much steam must be applied to the heater per hour. Okay, so your mass of the liquid is given, water is given, that has to be heated. Okay, so given that the temperature of the steam and the enthalpy of steam are constant, you need to find the amount of steam that has to be applied per hour to heat this water to a temperature of 100 degrees Celsius. Okay, so that's the question. I think it's quite clear and well understood, but again you can stop the question, pause the question whenever required, and if you require, stop the question pause the video right now, try it out yourself, and then look in the solution that I am discussing right away. Okay, so to solve this, again it's simple. We start with the steady flow energy equation again. Okay, so yes, okay, it's fine. So this is this is schematic representation of the question. That is there is a input of water and steam into the system, and the mixture of water and steam comes out of it. Okay, so the mass conservation equation would basically be W1 plus W2 is equal to W3. Okay. From the steady state equation, that is basically like this is the mass input, this is the mass output. So input has to be equal to the output for steady state. So W1 plus W2 should be equal to W3. Okay, quite simple. Now from the steady flow energy equation, we have that W1 plus H1 plus V1 square by 2 plus GZ1 plus Q dot plus W2 plus H2 plus V2 square by 2 plus GZ2. Again, these are added because these are at the inlet. Okay, there are two inlets and one outlet. Okay, and that should be equal to W3 plus H3 plus VT square by 2 plus GZ3 plus W dot. And since the system can be taken to be insulated, I'm not sure whether it has been mentioned in the question or not. You can just check it. Okay. So since there is no heat interaction mentioned, so we can take the system to be insulated and there is no work done. Okay, because this kind of system there is no shaft work done. So of course there is flow work, there is no shaft work. Okay, so there is no shaft work done. So this both Q and W dot, Q dot and W dot are equal to 0. And the kinetic energy and the potential energy are also almost equal to 0. So the equation of relevance are W1 H1 plus W2 H2 is equal to W3 H3. And if you see, this equation is something that becomes of quite huge relevance when dealing with heat exchangers. Okay, so we have that from mass conservation, W3 is W1 plus W2 from this equation. So you will have W1 H1 plus W2 H2 is equal to W1 plus W2 times H3. Okay, so if you now replace the value of all the known terms, that is W1, H1, H2 and H3, and you will only left with the unknown to be W2. That is something that we need to find out. Okay, so if you do that, you will get 4.2 times 313.93 plus W2 times 2676 equal to 4.2 plus W2 is equal to times 419. So from that you will get W2 is equal to 0.196 kg per second. So if you multiply it with 3600, that is 3600 seconds per hour, so we will get W2 as 705 kg per hour. Okay. So now let us look into the next question. Okay. A steady flow in a steady flow apparatus, 135 kilojoule of work is done by each kg of fluid. Okay, the specific volume of the fluid, pressure and velocity at the inlet are 0.37 meter cube per kg, 67 kilopascal and 60 meter per second. The inlet is 32 meter above the floor. Okay, so in this case now the potential energy change will become relevant, and discharge pipe is at the floor level. Okay, is at the floor level. Discharge pipe is at the floor level. The discharge conditions are 0.62 meter cube per kg, 100 kilopascal into 70 meter per second. The total heat loss between the inlet and outlet is 9 kilojoule per kg. In flowing through the apparatus, does the specific internal energy of the system increase or decrease? Okay, increase or decrease, I need to find out, and by how much? Again, it's a very simple question. Again, just a simple application of steady flow energy equation. So ideal practice would be start with the entire steady flow energy equation, and since all the terms are already there, so I think there's nothing that you can cancel out. So the thing that you need to find is the change in the internal energy. Okay, so U1 minus U2. So you need to find U1 minus U2. So again, you can pause the video here, so you can try it out yourself and then look into my solution. Okay, so I will start discussing the solution now. So you have, which is the solution? Okay, so it's discussed. Yeah, it's the first one. Yeah, this one. Okay, so this is your schematic diagram for the question. There is a net work output of 135 kilojoule, and net heat leakage of minus 9 kilojoule. Heat is coming out of the system. So these are the inlet conditions, inlet parameters. Okay, and these are the outlet conditions. Okay, so from then you need to find whether the internal energy of the system increases or decreases. Okay, so again, since they want internal energy, so you will have to write in terms of internal energy and your flow work. Okay, so this is basically H1, but since they asked us to find the change in U1 and U1 minus U2, so you need to dissociate this enthalpy in terms of the internal energy and the flow work. Okay, so u1 plus p1 v1 plus v1 square by 2 plus gz1 plus q dot is equal to u2 plus pu2 v2 plus v2 square by 2 plus gz2 plus w dot. So you need to find u1 minus u2. Okay, or u2 minus u1, whatever you may like. So if u2 minus u1 is positive, it would mean the internal energy has increased, or and if it's negative, it would mean that the internal energy has decreased. Similarly, if u1 minus u2 is positive, it would mean that the internal energy has decreased, or if u1 minus u2 is negative, it would imply that internal energy has increased. Okay, just vice versa, it's understandable. So if you rearrange the equation and separate out this u1 minus u2, you will have p2 v2 minus p1 v1 plus v2 square minus v1 square by 2 plus z2 minus z1 g plus w dot minus q dot. So if you substitute all these relevant values of the parameters in these terms, you will get that u1 minus u2 is 20.136 kilojoule per kg, which would imply that the internal energy of the system has indeed decreased. Okay, because u1 is greater than u2, so the internal energy of the system has decreased. Okay, so for the last question, again is simple, match the following. So you are given all the devices that we already discussed, right, and the corresponding values the different energy equation are given. Then you need to match the following. Okay, so let us try it out. Okay, you can stop the video here and try it out, but let me just try it on myself as well. Okay, so nozzles and diffusers, I know that velocities are quantity of relevance and enthalpy will also be there, so A should be matched with Q. Turbines and rotary compressors, I know that the work done is relevant, so the work done term has to be there, so it should be this one. Heat exchangers, there are multiple inlets and outlets, so and enthalpy is relevant, important parameter, so P should be there, and the one left is this one, so this should be them. So my solution would be A, Q, B, S, C, P, and D, R. AQ, BS, CP, DR. AQ, BS, CP, DR. So this is your correct option. Okay. So okay, then that's all for today from my end. Again, I'm sorry for postponing these sessions, but I will make sure that I upload all the videos that are required for this course, and you can take that for your reference. Okay, sorry again for the inconvenience caused, and let's all meet in the next week sessions. Okay, for the week 8 session. Okay, thank you and have a nice day.